So reminder, an optimization problem is an application of finding an absolute extremum, either an absolute minimum or an absolute maximum. And extrema can occur at endpoints if endpoints are known, or at a location of a relative extreme value, which is a critical point. So a place where the derivative is 0 or is undefined. So we talked about these steps in the last video. We're going to use these steps to answer another problem. This one appeared on a free response question in 2006. All right. So you have somebody on an exercise machine and you know the rate at which they're burning calories. It's given by this function f of t. F of t is shown here in this picture, and it's piecewise defined. The first piece is polynomial, and then the other pieces all happen to be linear. So our question, for the time interval 0 to 24 minutes, at what time t is f increasing at its greatest rate? So step 1, we need to figure out what quantity we're trying to optimize and whether we're trying to minimize it or maximize it. So we want to know when f is increasing at its greatest rate. So the rate at which f changes, so the rate at which f increases or decreases is called f prime, and we want to maximize f prime. So the rate which f of t increases and or decreases is f prime of t. So we're trying to maximize f prime of t. So I'm going to need an expression, a formula, a function to describe f prime of t. So since f is piecewise, f prime will also be piecewise. Let's see how we can do this. So that first piece, which was polynomial, it's pretty easy to find the derivative. And then since the other pieces are linear, I found the slope of all the other pieces. Now, any place where f has a corner, and there's 1, 2, 3, 4 of those corners, f prime won't exist. And that's the reason why in my little domain statements, in my piecewise definition for f prime, I don't have any or equal to signs. Because if I use an or equal to sign, I'd be giving a derivative at one of those corners. The corners have no derivatives. The f has no derivative at its corners. So step 3 is to find the derivative of that function. So f prime is the one we want to optimize. So to find critical points, we're going to need f double prime. So take that last look at f prime. It has one piece. That first piece is polynomial. I'll be able to find its derivative by using the power rule. The rest of the pieces from time 0 to time 24 are all linear. So when I take their derivative, I'll have 0. So my f double prime of t kind of looks like this. There you go. So I collapsed that down. Instead of having 0 over 4 different separate intervals, the second derivative is essentially 0 from time 4 to time 24. And now we need the critical points of f prime. So f, that's a typo, thank you for your patience. F prime has critical points where f double prime of t is 0 or undefined. So I'm going to set that first piece equal to 0 and solve for t. I get 2. And, kind of like the first time this has happened, every t in between 4 and 24 is a critical point because the derivative is 0 everywhere there. All right, so we're going to make our table of values. We're going to need to include any endpoints. 0, this is 0, and 24. We need to include the critical points, for sure 2. And then we need to think of a way to check, because we kind of had critical point everywhere in between in between 4 and 24. So just notice, if we're thinking about f prime, thinking about the slope of this graph, here the slope is 0. That's not going to be a maximum. Here the slope is 0. That's not going to be maximum. Here the slope is negative. That's not going to be my maximum. So the only one we have to really consider adding to our list is pick any t value in between 12 and 16 and use the slope value from there. So that was 2 minus 9 is 6 over 4. I don't know. I'm just going to write 12 to 16. On that time interval 12 to 16, I need, this is why I write it down so I don't get confused, I need f prime. F prime is going to be the slope of f, and we said that that was 3/2. All right, so what about at time 0? I'm going to need f double prime of 0. No, I'm going to need f prime of 0. This is why I label that so I don't get confused. So f prime of t is going to be, so I wrote in my f prime rule. Well, this is the first piece of the f prime rule, just so I can remember. So when I replace t with 0, that's going to be 0. When I replace t with 2, that's -3/4 times 4, so -3 plus 6 is going to be 3. And then when time is 24, I notice my slope is negative anyway, so was that -3? All right, so from my list, I can see that I wanted to maximize f prime, so I made a table of values. Time 2 gives me my maximum f prime. So now I'm going to write up my answer the way I would on the AP test. So here's what I wrote. Candidates for the time t at which f of t is increasing at the greatest rate are the endpoints t is 0 and t is 24, and the critical points of f prime. F of t is increasing at its greatest rate at time t equals 2, because f prime of 2 is 3, which is greater than the value of f prime on the interval 12 to 16. If you're asked to justify your answer, I might have gone a little overboard. They just said to show the reasoning. On the AP test, you'll be asked to justify your answer on some kinds of optimization problems, in which case you will have to state why it was that you only had to check at certain t values. And that's because we know that the candidates for the location of the absolute extrema are the endpoints and the critical points of whatever function it is that we're trying to optimize. All right, so one more problem. We're trying to maximize the area of a right triangle with hypotenuse 5. So here's my right triangle I've drawn on the hypotenuse. Question 1, we want to maximize area. So I'm going to have to write an expression for area. I'm going to start with the area of a right triangle, which is 1/2 base times height, area of any triangle. There's a little bit of a problem because right now that has 2 variables in it, and I want a formula that has 1 variable.